This is trajectory optimization for a batteryless solar-powered unmanned aerial vehicle. The prototypical solar aircraft that people tend to think of are these large, slow, kind of ultra-efficient, super delicate aircraft like you see in these three images. However, with the proliferation of cheap, efficient, lightweight solar cells, we can now build much smaller and faster designs. On sunny days, we even have excess power, and there's no need to carry such a large battery or any battery for that matter. Here's an example of a batteryless solar-powered plane. As you can see, it has plenty of power, and it's quite acrobatic and maneuverable. So as we saw previously, batteryless solar-powered planes can be extremely fast, maneuverable, and acrobatic, and thrust and speed depend on actually the angular position relative to the sun. Therefore, we have an interesting dynamical system on our hands. In this study, we have formulated a direct transcription optimization problem that attempts to maximize the altitude gain. But we need to set up the problem carefully. In particular, we need to add a control cost in order to reduce the solver's instability, and we also need a lift constraint to ensure that we're producing realistic trajectories. And now for the results. Here you can see an aircraft maximizing its altitude gain at solar noon. So you can see on the right side of the image, the solar rays are coming from the top right, and the aircraft immediately turns to fly away from the sun in such a way that it's banked in a direction that's perpendicular to the sun rays. And this is a good policy for optimizing the energy that it can acquire from the sun rays. Now we see the aircraft flying in more marginal conditions closer to sunset, so there's a lot less power available. And you can see it takes this snaking trajectory in a way that it's able to bank towards the sun for part of the trajectory and has to bank away for another part of the trajectory. A few next steps for this study include increasing the robustness of the solver so that we can discover more interesting trajectories. In addition, we would like to classify the seed trajectories by the local optima they produce. So by seed trajectory, we mean the initial trajectory that we give to the solver. And in general, the solver only produces local optima, so the solutions are highly dependent on these initial trajectories. So we'd like to understand these a bit better.